Hello everyone, this is Group 18 and we're back with another presentation for operating systems. We have some text file to simulate our processes. The structure of the text files are, we have the number of processes on the top, and then we say we have this many processes, their arrival time, burst time, and the priority as the tiebreaker. We have a graphical user interface where we can select the algorithm, specify the time quantum, context switch time, etc.
So the following algorithms are heavily based on this concept of process states. The processor is gonna be in one of three different states. It's gonna be idle, which is can actually be idle, not doing anything, or is the state in which we make it select a new process to run. Then it could either be running or it can be context switching. But there's a caveat for this. It will only ever be running or context switching if it has to run something or context switch for more than one timer, 1 second. Otherwise, because immediately after we're gonna pick a new process anyway, we're just gonna stay in the idle state, which is the pick a new process state.
For the file reader and the initialization, we went with creating two classes, one for the process to be able to initialize every single value, such as the process ID, the burst time, the arrival time, and etc. And for the class process reader, we made it work so that it selected the file. It made sure that the file was compatible with the try clause and made sure that the file was able to be open and had the same formula as in the little picture that we saw in the previous slides. We made it so that it iterates through every line so it can detect every number of processes, and that way we can iterate through them and be able to run the proper algorithm with it.
So, with respect to first come, first serve follows first come, first serve logic, meaning it takes the first process that is entered ready queue and runs until completion. This is a non-preemptive algorithm and sorts according to arrival time. And should arrival time be the same, there are tiebreakers for best priority and also for lowest process ID. This algorithm keeps track of processor states and the simplest algorithm of the four.
For the shortest job first, or SJF, it is also a non-preemptive algorithm, and it is very similar to the first come, first serve algorithm. The only difference is that instead of sorting by the arrival time, it sorts by the burst time. In other words, it'll take the process in the ready queue that has the smallest burst time so that it will finish first and before any of the other ones. Just like the first come, first serve, it also uses the same tiebreaker.
Shortest remaining time first is the first of the preemptive algorithms. That means interrupts can happen. So it's pretty much shortest job first, but with interrupts, and that means context switching is also involved. Not only context switching, we also need to keep track of a quantum time to see how often to check the ready queue with a process with a less remaining time. And then we'd run that instead after context switching.
Round robin is also a preemptive algorithm, and it's very similar to the shortest remaining time first algorithm, but in this case every process is selected based on the first come first served basics. In this case, the switch time works like an updated arrival time, where the ready queue is sorted based on the time that a process comes back into the queue.
So the back end of this program is mainly driven by PyQt6. PyQt6 is what allows us to integrate the graphical user interface. And on top of PyQt6, we also have matplotlib running on top of PyQt6. So we have a little window reserved in PyQt6 to store the matplotlib graph. And then we added an extra thing too. There's some background music, which is made possible with the Pygame module.
To start off with our code, we've decided to create a class process to be able to initialize every single one of our variables that we are going to use for our algorithms, such as the process ID, the arrival time, the burst time, the priority, the remaining time, and etc. If we continue down to the process reader, this class is used for us to be able to select the proper file for reading to then use to implement into our code so we can see the graph resulting from that text file. For the select file method, we first verify if the file that we picked is compatible with our code. So we will try to run the file to see if it does accept the txt file that we wanted to accept. If it doesn't, it runs an exception and it prints out an error. But if it does take a txt file and it does work, then it runs through a txt file and iterates through every line to be able to grab the process ID, the arrival time, the burst time, and the priority, so that we can implement those into the selected algorithm. At the end of the process reader, it returns a list of objects of our processes.
We begin by defining our main FCFS class, for where all of our variables are redefined and our logic is stored in various methods. In our scheduling method, down below, we begin by defining our ready queue for the process and defining some more key variables, such as our timer and our tempo variables. Timer's just a timer, and tempo will be used to advance all of timings used in our program. Under this large while loop, a little lower, first we check for the processes to see if they arrive constantly, and then we sort the ready queue to make sure we are always running the processes in the correct order. Then we check the state of the processor. For FCFS, context switching never arrives, so our only states will be idle and running. Here we have a check. It's a simple if-else, because the processor is only going to be in the idle state, meaning we're going to pick a new process to run, or else it's going to be running. After it picks a process, it will run the ones that have the smallest arrival time until they are finished. Notice the change of state to I in line 69. Finally, when there are no processes to run in the running queue, and there are no more processes to be run in the future, we will exit the code with our break command.
When it comes to SGF, the code is very similar to the first come first serve algorithm. Everything along the codes for the initialization and the schedule remains the same, other than the sorting of the processes in the ready queue. For FCFS, we use the arrival time for the sorting, but for SGF, we are actually using the burst time, since we are doing the shortest job first. And thus, whenever it is moved into the ready queue, we use the burst time as the factor to determine which one goes through first before the other one. And if there is a tie in between them, then we use the priority to be able to determine which one goes through first.
Sure, this remaining time first, as we said earlier, is gonna have a very similar logic to show this job first. I said it's gonna consider the burst time, but in this case, we are gonna consider the burst time over time, because as the process does things and it saves context, how much it needs to work, it's gonna be less. So we have an extra variable in the process that we're gonna be using, which is the remaining time instead. Other than that, because we introduced interrupts, we're gonna have to finally use our context process state. The program runs a lot of very similar checks, but there are some important other ones that we're gonna have to mention. So for example, if the quantum is only of 1, we're gonna constantly be checking for a new process to run. So we're never really gonna go into the running state. We're just gonna be either choosing a new process or context switching to save it if it's necessary. And for some reason, the context switching is also of 0. We're just gonna be constantly in the run idle state, which is we pick a process, we run it for 1. We pick a process, we run it for 1. If, however, those numbers change and they're bigger, that's when the running and context switching states come in. Context switching state is very simple. It's just gonna run until we're done context switching. Every process has a variable that keeps track of that. And for running, the same. We're gonna be running until one of two things happen. We're done, or we reach our quantum. In which case, if we reach our quantum, we may have to context save, or we may not. But usually we're just gonna go back to the idle and pick up your process again.
For the round robin algorithm, the code is a lot similar to, or the logic is a lot similar to the shortest remaining time first. But here, switch time is the most important thing. This is the updated arrival time, like I've explained before. It keeps track of the process when the process joined or rejoined the ready queue last. So the processes are run in order. And if we show our sorting here of the ready queue, we can see that it's actually being sorted by the switch time, not the arrival time, but the updated arrival time, followed by the biggest priority as a tiebreaker, and the final tiebreaker being the smallest process ID. And this guarantees that everything is running in order.
So this GUI class is what formulates the GUI, sets up the window size and everything, and then executes the GUI. Okay, so this main window class is what controls the window for the GUI. And then you see this self.mdi area. That MDI area is a special area to hold the graph once the graph appears on the screen. So as you can see, we have two buttons, and then the .click connect is what, when the user clicks the button, that processes the information from the GUI interface into a function call in Python. In this case, we're calling for when you click update graph, it's going to go to the update graph function. So update graph, essentially, it does a check. If the graph is already on the screen, then just update the graph. Otherwise, we gotta form the new window and create the graph. Update graph then runs select algorithm. The select algorithm is what chooses which algorithm we're going to run. And each of these algorithms, it creates an object for to store the algorithm, and then the self.stats is what retrieves the data from the scheduling function in the algorithm. This data is going to be a two-dimensional array which contains the process ID number, or in the case that there was idle or context switching, that replaces the process ID number, and the time at which this happens. So here we see this graph class. This is essentially what plots our graph on the screen. Process ID will be on the y-axis, and then we have time on the x-axis.
So when we run the main.py file, we can actually see the Pygame starts and we can hear the background music, and we have the file dialog where we can specify the test files. And here we specify our context switch time, the quantum time, our algorithm of choice, and we can show an update graph or input another test file if we wanted to. So if I hit show an update graph now, we already have this test file selected. We have this I here, which is showing the idling state of the CPU. So this process actually starts running at here. If I change the algorithm to shortest job first and hit update graph, it actually updates the graph. For example, we can give it another test file and hit show an update graph. It actually changes the graph here. And if we change it to round robin, and we can specify the quantum time and context switch time, and if we hit update, we can see the graph for our round robin algorithm. We can change it to maybe another file and hit show an update graph. We can see our graph is updating to that. The C is where the process is context switching, as we can see on the graph right here on the x-axis, on the y-axis.
Thank you for watching our presentation about the 4 algorithms. This is Group 18 signing out.